Good day, students. In this clip, we're going to be going over some examples to review differentiation. We're going to be looking at the differentiation using limits, differentiation of graphs, and then the average value, and also using the differentiation rules to find derivatives at certain points. All right. So let's take a look at question number one. So for question one, we are to express the limit as a derivative, express the limit as a derivative, and evaluate it. Evaluate it. All right. Okay, so the limit expression under consideration for number one is the limit as h approaches 0 of 2 raised to the 2 times negative 1 plus h minus 1/4. And this entire thing divided by um, h. Okay. Now, what is this in derivative form? All right, first of all, let's go over the formula for how to express the derivative as a limit. So formula. So the derivative at any value x, f prime of x, expressed using limits, is the limit as h approaches 0 of f of x plus h minus f of x over h. Okay? This is the derivative at any point x. Well, this limit doesn't have any x in it because it is a derivative evaluated at a point. So what is the derivative evaluated at a point using limits? F prime of a. F prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a divided by h. Okay? So basically, if you evaluate the limit at a point, instead of x, you have a. So if we take a look at this expression right here, what is the value of x? Or where is x positioned? Well, guess what? Whatever you're adding to h, that should be a telltale sign as to what x is. Okay, in this case, this is x. Okay, x is having a value of negative 1, so we're evaluating the derivative of a function, of some function at x equals negative 1. Alright? So with this information, we can easily tell that f of x plus h is going to be this function, but instead of negative 1, I'm going to put h. I'm going to put x, okay? So it's going to be 2 raised to the 2 times x plus h. Alright, so this is the function that we're dealing with. Alright, so this is f of x plus h, then what must f of x be? Well, you just simply replace x plus h with x, so f of x is going to be 2 raised to the 2x. So this limit in derivative form can be written as we're to find f prime of negative 1 where the function f of x is equal to 2 raised to the 2x. Okay, so this is our first answer, evaluating the derivative of the function 2 to the 2x at negative 1. The problem also asks us to evaluate the limits, the derivative. So let's find the derivative of this function at x equals negative 1. So to do this, first thing we'll do is differentiate the function, and then we'll plug in negative 1 into the derivative, all right? So the function f of x is 2 raised to the 2x. So the formulas that we're going to use are as follows. So formulas, we have two functions here. We have the exponential function composed with the linear function. All right, so we're going to have to use a chain rule once to go from the exponential function to the linear function. All right, so let's start with the outermost function, d dx of 2 raised to the u. We're using u for the power because the power of this exponential function is a function, so that indicates the importance or the necessity of using the chain rule. All right, so the derivative of 2 to the u using the rules, is 2 to the u, ln of the base, which is 2, du dx. Okay? Alright. Now, then the innermost function, which is a linear function 2x, d dx of 2x is equal to 2. You don't need the chain rule here because this is not a composite function. Okay, so putting these two together will tell us what the derivative of this function is. So we can see that prime f prime of x is going to be 2 to the u ln 2. So it's u in this case is 2x, so it's going to be 2 raised to the 2x ln 2 du dx is the derivative of 2x, and we already found out what that is, which is 2. So times 2. Okay? Alright, so we're asked to find the derivative at -1. So we're going to find f prime of -1. F prime of -1 is equal to 2 raised to the 2 times -1 times the natural logarithm of 2 times 2. Alright? So let's simplify this. This becomes 2 ln 2 over 2 raised to the -2 is 2 squared. Okay? So that equals, using the properties of exponents, we're going to have 2 times the natural logarithm of 2 over 4. Alright? 2 goes here 1, 2 goes here 2. Your final answer is the natural logarithm of 2 over 2. So that's the derivative of the function 2 to the 2x at x equals -1. Alright, let's shift our attention to question number 2. Question 2. Question 2 is as follows. It's going to be a function example where we're going to make use of the product and quotient rules. Okay, so for number 2, suppose f and g are differentiable at x equals 2, and f of 2 is equal to 3, f prime of 2 is equal to 5, g of 2 is equal to -1, and g prime of 2 is equal to 3. So the task is to find A, or to find d dx of 4fg, and B, we're to find d dx of 3g over f. Okay, we have to find this one at x equals 2. Both of them, we need to find both of them at x equals 2. Okay. All right, let's do the A part. So the A part, we're going to find the derivative d dx of 4 times fg. Using a constant multiple rule, I can factor out 4 from the derivative, so we kind of have 4 times d dx of f times g. Okay? Alright, so the formula we're going to be using here is the formula that involves the product of two functions. So the formula is the product rule. Alright, so formula uv prime is equal to v u prime plus uv prime. Okay, in this case, f is our u and g is our v. Alright, so let's apply the product rule here. If we do that, the derivative is going to be equal to 4 times times v, which is g u prime f prime, plus u, which is f v prime, which is g prime. Alright, so we're evaluating the derivative at x equals 2. So if we're evaluating it at x equals 2, we're going to have 4 times, it's going to be 4 times g of 2 times f prime of 2 plus f of 2 times g prime of 2. Okay? Now all we just simply do is plug in the values of the functions and their derivatives into this expression, evaluate it, and that'll be our final answer. Alright, so we're going to have 4 times g of 2 is negative 1 times f prime of 2 is 5 plus f of 2 is 3 times g prime of 2 is 3. Alright, we'll work that out. We're going to have 4 times negative 5 plus 9, and our final answer is going to be equal to 16. Alright, so there you have it. Now let's do the B part. Let's partition our workspace so we don't get mixed up. For the B part, we're looking for the derivative ddx of 3g over f. In this case, we can use a constant multiple rule and factor out 3, so 3 times the derivative of g over f. Alright, so what formula are we going to use here? We're going to make use of the quotient rule. Okay, so remember what your quotient rule is. U over v prime is equal to vu prime minus uv prime divided by v squared. Okay, in this case, g is your u, and that's u, and f is our v. Okay, so if we apply the quotient rule to this situation, the derivative is going to be 3 times vu prime is going to be fg prime minus uv prime is going to be gf prime over f squared. Okay, so if we evaluate this derivative at a point, namely at x equals 2, we're going to have 3 times f of 2 times g prime of 2 minus g of 2 times f prime of 2. This entire thing divided by v squared, and we know what v is f, so it's going to be divided by f of 2 squared. Okay, alright, now we're going to use the chart above to find the values of each function and their derivatives at x equals 2. So if we do that, we're going to have what are we going to have? We're going to have 3 on the outside times 3 times 3 minus negative 1 times 5. All this divided by 3 squared. So this is going to be equal to 3 times 9 plus 5 over 9. Okay, so notice 3 goes into 9, right? So we can divide that out. We have 3 goes here 1, 3 goes here 3 times. Alright, so we have 9 plus 5, which is 14. 14 over 3. That's our final answer. Okay, so that's that. Alright, let's take a look at question number 3. So for problem 3, the instructions are as follows. It says for the given velocity curve, draw, or basically sketch, draw the related acceleration curve on the same axis. Okay, alright, so there are two ways you can do this. You can think about the slope of a tangent line at different points and then you graph the slope, which is pretty complicated and time consuming. Or alternatively, you can try and think about the function that generates these graphs, differentiate those functions, and then sketch the graph of the derivatives. Okay, so that's the approach I'm going to use. If we take a look at the function here on the left side right here, this piece looks like a cosine function. Okay, a cosine function with a period of 2 2 pi, and it has a period of 4 and an amplitude of 2. Okay, so let's just call this is like a cosine function. So v of t is equal to cosine t. This is not being 100% precise. I'm just going to act as though this is your standard cosine function, all right? So on this interval to the left, this is an equation that models the behavior of the curve. And on the right side, it kind of looks like a quadratic function, right? So on the right side, let's say this is your velocity function. V of t is equal to t squared is a quadratic function that has been shifted 2 units down, so t squared minus 2. Okay? So in order to find what the acceleration function looks like here, let me change my colors real quick. So let's call the velocity function on this side, on the right side, v of t equals t squared minus 2. So on the left side, to find the acceleration function, remember your SVAJ continuum. If you're going from velocity to acceleration, you just differentiate once, okay? So your acceleration function is going to be the derivative of cosine, which is negative sine t, okay? And then for this interval from 0 to infinity, your acceleration function is going to be 2t. Now, what does the negative sine function look like? We know that sine starts from the origin, and then it goes up, down to the center, and then down, and then back to the center. If you're doing the negative, we're going to do the reverse. So instead of going up, it goes down to the right and up to the left. So it's going to go from here, it's going to max out there, and then come back to the center right there. All right? So it's just a portion of your sine curve, so we can connect the dots like that as best as we can. And then that's a sketch of the derivative of this portion. We can see why that's the case. Here the derivative is 0, and then here the derivative is positive 1, and then here the derivative is 0. You can see how that behavior is replicated by the component of the negative sine t curve from 1 to negative 2. Alright, and then here this is like a quadratic function shifted 2 units down. The acceleration function is given by the line 2t. So the slope intercept, the y-intercept is 0 and the slope is 2. So let's go ahead and graph that here. So let me make it the blue line. So we're graphing it from here, from the center, because the y-intercept is 0. We're going to rise 2 and run 1. So that's what your line will basically look like. Alright? So this function we have just drawn is your acceleration curve, given this red velocity curve right here, okay? So the graph in blue is a of t, and the graph that's in red is your velocity function v of t. Alright, so there you have it. Alright, let's take a look at question number 4. So for problem 4, instructions are as follows. The following chart, this chart provided down here, following chart gives the position s of t of a moving body, in seconds. Okay, so we have this chart right here. So the task is A, we're to find the average velocity, from 3 to 17. Alright, from 3 to 17. The B part, we have to approximate the instantaneous velocity, velocity at t equals 8 And then part C, we're to approximate the instantaneous acceleration at t equals 8. Okay? Alright, let's start from the first part. The A part is to find the average velocity. Okay? So before we do that, let's write down the formula for the average velocity and average acceleration. Okay? So formulas. So the uh, average velocity is equal to delta S delta t. So let's say we're looking for the average velocity on an interval AB. Okay, so it's going to be given by the slope of the secant line through those 2 points, A comma S of A and B comma S of B. Okay, so to find the slope, we're going to do S of B, which is like your y2 minus y1, which is S of A, divided by um, x2, which is b, minus x1, which is a. All right, so that's your average velocity. And you wanted to find your average acceleration. That will be the slope of the secant line using your velocity coordinates as your points. Okay, so that's going to be delta v, delta t. So let's say we were evaluating it from A to B, for example. It's going to be similar to this, only that we're going to be using the velocity functions to compute our points. Okay, so it's going to be v of b, that'll be our y2 minus v of a, that's y1, divided by x2, which is v minus x1, which is a. Alright, so these are the formulas we're going to be using for these problems, alright? So part A asks us to find the average average velocity on the interval 3 to 17. So let's write that down. Average velocity. The average velocity is basically given by, let's use this formula right here, delta S over delta T evaluated from 3 to 17. That's what the problem asks us to find. Okay, so if we do that, we're going to have S. In this case, B is 17, A is 3. Okay, so S of 17 minus S of 3. That divided by 17 minus 3. Okay, divided by 17 minus 3. Alright, so we just use our charts to figure this out. So if we look at our chart, S of 17 is 26, minus S of 3 is 6, 17 minus 3 is 14. If we reduce this, we're going to have 20 over 14. If we divide top and bottom by 2, we'll have 10 over 7 as our average velocity. It's going to be 10 over 7 feet per second. Okay, so do not forget to include your units in your final answer. So 10 over 7 feet per second. Alright, let's shift our attention to the B part, part B. We're to find the let's approximate the instantaneous velocity at t equals 8. Alright, so the instantaneous velocity at t equals 8 can be written by v of 8. So v of 8 is basically can also be written as s prime of 8, the derivative of the position at 8, because you know the derivative of position is velocity. Okay, so we're going to approximate this. This is going to be approximately delta s over delta t evaluated from 5 to 10. Okay, how do we know that we're going from 5 to 10? Well, if you look at the chart, we're finding the average velocity. We are approximating the instantaneous velocity at 8. So we're going to pick a number before and after 8 so we can have the slope of that secant line to tell us what it is. Alright, so we pick 5 and 10 as the intervals around 8 to calculate the slope of the secant line on the position graph. Okay. All right. So that's how we have 5 to 10. Now let's go ahead and figure that out. This is going to be equal to S of B, which is S of 10, minus S of A, which is 5, divided by B minus A, 10 minus 5, using this formula that we had up here. Okay, so if we use our chart, S of 10 is 16, minus S of 5, which is 9, divided by 10 minus 5, which is 5, and then our final answer is going to be 16 minus 9 is 7 over 5 unit feet per second. All right, so this is your approximate um, instantaneous velocity at t equals 8. All right, so let's go ahead and box that. Okay, let's shift our attention to the last portion, which asks us to find the to approximate the instantaneous acceleration at t equals 8. All right, so for part C, we're looking for a of 8. So that is equal to what? Remember, if you differentiate your velocity, you get the acceleration, right? So this is equal to the derivative of the velocity at 8. All right? So in order to approximate this, we're going to be calculating the slope of a secant line using 2 points on our velocity time chart. Okay? Notice we're given here, we're provided with the position time chart. So we have to basically come up with the velocity time chart and then find the slope of a secant line around 8 to approximate our instantaneous acceleration. Alright, so to do that, we're going to be using delta V over delta T on what interval? What interval are we going to be looking here? Well, let's go up. We want to find the instantaneous acceleration. So what we have to do is we're not going to be using the time and position function. We need to use these two values and these two values to create a new chart, our velocity and time chart, and then we can use the slope of the 2 points we created to find our approximate acceleration. Alright, so what I'm going to do is I'm going to extend this interval a little bit. So I need an interval from here, and then I need an interval from here. Okay, so how do we find those? All we simply do is we're just going to average. Okay, so if I average these 2 times, I can have a point here that I can use to calculate the first point of my velocity, and then another point here. Alright, so to find the midpoint here, all we just do is average these 2. So this point is basically 5 plus 8 over 2 to get this point right here, which is equal to 5 plus 8 is 13 over 2. So that will be our lower bound of the point, less than 8, to make my velocity time chart. And then for this one, this point right here, we're going to do 8 plus 10, just average these 2. Okay, 8 plus 10 over 2, which is 18 over 2, which equals 9. Alright, so that will be my second time in the generation of my velocity time chart. Okay, so to find the approximate acceleration, we're going to be evaluating delta V over delta T from the lower interval we created, which is 8 plus 5 over 2. Well, let me write it the way I ordered it up there, which is 5 plus 8, I think I did. So the lower interval, lower boundary is 5 plus 8 over 2. That's going to be our A, comma, our B is going to be the average of the 2 upper values, which is 8 plus 10 over 2. Alright, so this is equal to delta V over delta T from, like we did upstairs there, from 13 over 2 all the way to 9. Alright, so now using our formula for average acceleration that we have here, we're going to be calculating V of B, which is 9, minus V of A, which is 13 over 2, and then that divided by B, which is 9, minus A, 13 over 2. Okay? Alright, so now we have a new problem. We have to now find the instantaneous velocity at t equals 9, and also the instantaneous velocity at t equals 13 over 2. Well, since we don't have these, we have to approximate. We're going to be using the approximate values here. Okay, so v of 9 is going to be, v of 9 is the instantaneous velocity at t equals 9, and that is equal to s prime of 9. Okay, so we have to approximate here. So to approximate here, we're going to be using delta s over delta t evaluated on an interval around 9. Okay, so what's the interval around 9? Let's scroll back up. The interval around 9 is 8 and 10. Okay, so we're going to be going from 8 to 10 to calculate the average velocity. Okay, so we're going to be going from 8 to 10. Okay, all right, so using the formula we went over it upstairs, we have s of b, which is s of 10, minus s of a, which is 8, divided by b minus a, which is 10 minus 8. So that's going to be s of is going to be 16 minus 12 using the chart over 10 minus 8, which is 2. So this is simplify this, we have 4 over 2, and it reduces to 2 feet per second. So this is your average acceleration, average velocity at t equals 9. Okay, it's an approximation. All right, and then we also need v of 13 over 2. Instantaneous velocity of 13 over 2 is the same thing as the derivative of the position at 13 over 2. We don't have the function, so we have to use an approximation here, okay? So we're going to be approximating delta s over delta t, evaluated on what interval is the question. So let's go back to the chart. We're working around 13 over 2, which is this boundary right here, so we're going to be going from 5 to 8. Okay, to calculate the slope of that secant line from to this point. So we're going to have the interval will go from 5 all the way to 8. All right, let's try that again, 5 to 8. Okay, so using the formula well, went over upstairs, we're going to be computing s of 8 minus s of 5 divided by 8 minus 5. Okay, so this is going to become 12. S of 8 is 12 minus s of 5, 9, divided by 8 minus 5 is 3. Okay, let's work this out. 12 minus 9 is 3. 3 over 3 is 1. So 1 feet per second. All right. All right, now we have all the information that we need to calculate our approximate instantaneous acceleration. So let's rewrite down what we had upstairs. So a of 8 is approximately v of 9 minus v of 13 over 2 divided by, let's do that again, divided 13 over 2 divided by, we had 9 over 13 over 2, right? We can write 9 as a fraction and find the LCD, so put 9 over 2 and times it top and bottom by 2. So times it by 2 and times it by 2. So that's going to yield, what's that going to yield? It's going to give us 18 over 2 minus 13 over 2. Okay? So using the results we got, v of 9 is 2 minus v of 13 over 2 is 1 divided by 18 over 2 minus 13 over 2 is 5 over 2. Alright, so in the numerator we have 1 times the reciprocal of the denominator times 2 over 5. If you multiply across, you're going to have 2 over 5. And the unit of acceleration is feet per second square. Okay, so that basically is your approximate instantaneous acceleration at t equals 8 seconds. Alright, so there you have it. But thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking here. And please post a comment to let me know what you think about this clip. And if you liked it, I'll appreciate it if you give me a thumbs up. And feel free to share with your friends. More clips can be found on microsoft.com/calculus. Thanks again for watching and have a wonderful day.